This is SCUDEM 5, Team 1149, Problem B, by Cephas, Storm, and Caitlyn Feldpausch. Introduction. Presenters. Myself, Caitlyn Feldpausch, from Carthage College in Kenosha, Wisconsin.
And I'm Cephas Storm, also from Carthage College, which is in the US.
Our coach is Yaple with Carthage College in Kenosha, Wisconsin. As you can see, while the bird goes around the wheel, it somehow manages to complete a full continuous revolution instead of going back down. How does this happen? The hypothesis is, when the bird reaches close to its apogee, it displaces its center of mass such that it is to the right of the wheel's center, allowing gravity to push it again and then continuing indefinitely. Our task is to derive a differential equation to predict this motion. Goals. Derive differential equation or equations modeling the motion of the bird. Explain the changes necessary to the initial condition to maximize amplitude. Can this occur if the apparatus is initially still with the weight at the bottom, or must an initial rotational velocity or specific position be applied? Describe the maximum speed the wheel can spin. Simplifications and assumptions. We are assuming this model is two-dimensional. There is no friction within their system. The changing position of the apparatus does not induce any force change on the system. The wheel and bird are attached and dependent on one another. The wheel is considered a hollow loop. In our model, we have an apparatus of mass m1 connected to a hoop of mass m, which is a simplification of a bike tire, of a radius r, and an angle theta from the horizontal axis. Additionally, we have a small mass inside the apparatus of mass m2, and an angle phi displaced from the angle theta. The mass m2 will act to displace the center of mass of the apparatus, or the bird as seen in the video, as it nears the apogee.
The simplest way we found to solve this is through a straightforward application of the Lagrangian formalism. The position of the apparatus is given by this, and which we call RM1, so that is the position of the main apparatus body. The position of the extra mass is given by this, which we call RM2. The velocity in general is going to be described by the derivative of these, but using intuitions from polar coordinates, we can make a simpler definition since we know that r is not changing with time. The only thing that matters is the angular velocity, and we get this and this for the RM1 and RM2 respectively. So in Lagrangian mechanics, all we need to find are the total kinetic energy, and the total potential energy, which are as follows. So to find the equation of motion, we can fairly simply apply the Euler-Lagrange equation and get this beautiful equation as you see here. This is a second-order differential equation, and its solution is not easy, and insofar as where it cannot be defined using just elementary functions, it's complicated. Although if we choose phi, which we'll describe later, to be 0 or something simpler, there is an analytical solution to it. So if our phi of t, which is an equation describing the motion of the extra mass with respect to time, is some constant or 0 more ideally, it behaves more or less like a simple pendulum in that it's just a mass on some fixed length. If phi of t is a more complex function, it becomes very difficult to solve, and not even Mathematica is able to solve it analytically. In our case, we will choose phi of t is equal to sine of theta times t multiplied by some constant, which is going to be the maximum displacement from the main angle. This, we chose sine theta because at its apogee, or pi over 2, this is going to be at its maximum. So this will allow the mass to be displaced over the center of the wheel. So in the simple case where our phi of theta is just 0, we can get some pretty simple pendulum dynamics. This is where it starts at theta is equal to 0. And this is one of the equilibrii, which is when it starts at the bottom, or negative pi over 2. It will stay at this position forever, obviously, since it's a stable equilibrium. If it starts at pi over 2, this is an unstable equilibrium, and in general, it will stay there, but if you give it any sort of nudge, either to the left or the right, it will start falling. So, optimizing initial conditions. So, to increase amplitude, we can increase the initial angle closer to the apogee, such that its maximum displacement is going to be bigger and bigger. If we start at the apogee, or pi over 2, obviously we will not actually get anywhere, so we can't do that. The equation for the maximum velocity, or rather angular velocity, is given by this. This equation was derived using some pretty simple energy manipulation. Since we know that the energy in the system is conserved, we can just set the potential energy at its maximum, and then when the bob is at the bottom, we know that potential energy is equal to 0 there, and we can use that to solve for kinetic energy, which is what you get when you do all of that. So the interesting case, so after trying to solve it numerically using Mathematica, this is what we get for the motion of the system when phi of t is equal to sine of theta times 0.1, which means that there is relatively small change in the angle at its pi over 2, but it does allow the system to increase to get over the apogee. So if you notice, the one problem we did have is that as time increases, the motion becomes arbitrarily fast, and it seems almost like a degenerate solution. Our hypothesis for why this is a problem, which is in this case, is perhaps either Mathematica is not simulating it correctly, and as time goes on, errors compound and compound over and over again, making it crazier and crazier, or something else that we have yet to find. More research would be needed in this case. The way we might be able to improve the system is, most importantly, adding consideration for friction and the various ways that the system might be able to lose energy. We did not do that. And that is our presentation. We hope you enjoyed it.